It's an honor to me being invited here and present our work at Peru. I'm from Peru. I'm a research assistant at CISMID. Uh, I represent the Geomatics laboratory. It's a scientific uh, institution of my country. This presentation corresponds to the session B, coastal engineering. To begin with, I'm going to describe briefly why did we why did we start this research? The research was the purpose of the research is to surpass the fluid simulation to VR integration. So it's supported by these three papers. The first one, it proposes a workflow in order to pass the simulation of different disaster hazards into a VR headset. This is really important because in the workflow used in this work, we applied it to our case in the Ancon Bay. And the second one chooses software to integrate the VR with the fluid simulation, which is Unity. And the third one is reference used led by my colleagues at Peru, from Carlos Davila. They made a workflow with the UAV flights and the tsunami simulation in order to have a high resolution tsunami inundation simulation in all our country. And also they did this research in the same uh, area of study that I'm going to present. The area of the study is the Ancon Bay, is in the north of Lima. Lima is the capital of Peru. As you can see, one of their outputs, it's a video of the tsunami simulation and the 3D model obtained by the UAV flights. The main challenge of our research is that the 2D plans, maps, and even videos cannot make a spatial context for the hazard of the tsunami, and also they cannot train the individual in order to take their own decisions when there is a disaster like this. This leads to low risk perceptions because the hazard has a scale and a really big danger that if the people don't experience themselves, they don't take the adequate attention. So, for example, here is an evacuation drill in our country in Lima. The people don't take the enough attention when there is these drills. So our work wants to contribution our contribution the contribution of our work is create this integration between the numerical simulation of tsunami and also use the 3D model obtained by the UAV flights, also known as drones, and also use this integration in order to create a first-person immersive experience for the public. Here we have the three main components are the UAV flights from the drones and the tsunami simulation, and then we integrate everything into a VR headset. This is the workflow proposed by the research led by my colleagues at CISMID. As I mentioned before in the paper reference, they create a workflow to join them, but for the tsunami inundation. But the first part is the high resolution data acquisition. They made two flights. The first one is the oblique photogrammetry flight, and the second is the nadir photogrammetry flight. The first one is going to be used for the 3D model, really high resolution 3D model. And the second one is going to be used for the inundation outputs that are going to be the ASCII files at each time step. In this case, the tsunami was modeled the time step of 1 minute. And this is our workflow proposed in order to join both outputs. We make the immersive VR integration from the 3D model obtained by the UAV flights we make some optimization because we need to achieve some performance targets. We optimize the mesh, which has the nodes, the edges, the faces, and the texture also, it needs to be fixed. I'm going to explain that later, but we did some techniques as UAV mapping and also change some material and shaders, and we obtain an optimized 3D model. And for the tsunami animation, we need to, from the ASCII files, we create a tsunami key shape at each time step. And after some process, we have the tsunami 3D animated object, and then which can be joined with the optimized 3D model. And then we create a VR integration. I'm going to explain the first component of our work. Um, the first part is the UAV flights. As I mentioned, we have two flights, the nadir photogrammetry, which can uh, obtain a wide area than the oblique photogrammetry for the case of our study. The nadir photogrammetry is like a perpendicular obtained of data. It's a flight perpendicular, and the oblique photogrammetry is with different angles in order to have a higher resolution for a 3D model. And this is a video where is the 3D model with high resolution obtained by the oblique photogrammetry. And the second component is the numerical tsunami simulation. From the nadir photogrammetry flights, we obtain the digital surface model and the digital orthophoto map. Both of these inputs need to be processed in order to obtain the digital terrain model and the land use data. And both of these are inputs for the tsunami inundation. And also for the tsunami generation, we use the CADAS model, and for the tsunami propagation, we use the Tsunami N2 model and the bathymetry data. Here is one of the outputs of their investigation. They recreate this video joining both of them, but as I mentioned before, it's one video. It's not an immersive experience. That is our main goal of this research. Here is the area of study of Ancon, and here is the cemetery, which is the safe. Here is the sorry. Here is the worst case of inundation, and here is the inundation map also as an output. And this is our third part that we're going to explain from here on. The immersive VR platform that we are going to propose in this research uses the both inputs of the last components, the 3D model and the ASCII inundation files, to join them into a game engine, also mentioned in the state of art, Unity. We use the library of OpenXR, and then we want to create an independent VR application to present the model to the people. So to make a VR independent application, we need to remember that the VR software, I mean the VR hardware has some limitations because the model is going to be displayed in the hardware of the VR headset. So in this case, we use the MetaQuest 3. To have the minimum FPS, we need to have from 1.3 to 1.8 million of faces, or even if it's less, it's better for our purpose. And then the optimization we first optimize the mesh. We can see here from the table that the 3D model obtained by the UAV flights has a lot of vertices, a lot of edges, a lot of faces. And as I mentioned before, the performance target, in order to have the 72 FPS, we need to reduce it with some processes. For example, we use the Decimate. We use another software of 3D model, a 3D model software. We use Decimate. We remove hidden objects that are not going to be seen, such as areas that are hidden, and also hidden areas that are not going to be deployed in the VR headset. And from the texture, we make some process that is called baking from AKUV texture, because from the UAV flights, we obtain a lot of photos from a lot of photos in 8K resolution, and we need to reduce it to 4K. And for the tsunami animation, as you can see here, this is our inputs. This is the ASCII obtained from the inundation part. And also we pass it into the 3D software. And then we create the key shapes. This is the tsunami with the key shapes. And here we have some no data values. And we can change it, but for the purpose of this study, we leave it like this. And we cannot change it because it upgrades from at each time steps. We need to leave it like that. And this is the tsunami at the game engine by itself with the material. The results are here, as you can see, we obtained the integration, and we have the third-person view. As you can see, there are some there are some parts that can be fixed, but we reach the integration. And also here is the evacuation part. From here you can see that we can see the tsunami in first person, and also we are in the 3D model by itself. We can touch some things of story. It's some kind of abstract that we can touch the model, we can watch the model in first person, and also we reach the 72 FPS. We present some parts of this work into different public fairs, and also in the recent facilitation, we have a risk awareness center at CISMID where we share our work. Some limitation and future work. The limitation part, as we watch it in the video, are some quality and mesh noise. And this is because the Unity by itself, the software that we use, makes a loss optimization part that reduces a lot, reduces more than we reduce it by itself, and create this type of things. For example, here the window cannot be seen, and also here there is some mesh. The mesh is the form. Unity by itself, create this optimization in order to be deployed into independent VR into a VR independent application. So, but remember, we need to remember that the area of study is a wide area. We cannot we solve the problem of needing to create one by one each object. We just literally drag and drop the 3D object. So it reduces a lot of work time. For future work, as we have the workflow, we can create the automation and the technical improvement. Also, for the future, after this work will be finished, we can make some survey at different public fairs or at the awareness center at our laboratory to have the people risk perception and the social impact of our work. And just to conclude our work, we succeed in the successful integration of the tsunami numerical modeling and the UAV flights. This work hopes to be a baseline for different new works and enhanced visualization. The people here can watch in first person how the tsunami comes, and also he can play in their own area of study, in their own houses. And the optimization balance. Although there are some, we optimize the mesh, we optimize the texture, but we have some limitations, and this is because of the main software by itself. It's something that we need to correct in the source code of Unity. So we hope in the future that we can fix this problem. And just acknowledgement, this work was supported by the National University of Engineering, and also the Research Institute of the Civil Engineer faculty. This work was also presented as a part of a startup on our faculty. It was called VR Tsunami. And this is our work. This is our team. We really thank our team for their work. And we hope you enjoy the presentation. Thank you very much.